Welcome to the final chapter of Mathematics for Physicists 2. This chapter, let me say this from the beginning, is not relevant for the exam, and none of this will be asked for in the exam, but I will present you some really important theorems in this chapter, because this is kind of, I'm collecting some important theorems that are kind of the climax of multivariable calculus and the most important theorems there, because we shall see some really deep theorems that have lots of applications throughout the sciences, physics, geometry, calculus, and so on. And unfortunately, in this course, I don't have enough time to go into details there and to really explore the applications there in many different ways. But I will give you an overview and I will kind of give you motivating examples for each of these theorems. The structure of this chapter is a little different. I've called it the implicit function theorem and its friends, because the implicit function theorem is kind of the biggest of the theorems we are going to see. But there are some other related theorems, and I have structured the sections differently. Namely, each section will present one of these theorems in an explicit way. And in each of these sections, we will take a look at this respective theorem and give an application and an example and compute things with that theorem, so you get an idea of what's going on. So, what's the motivation for this? So let's start off very simple, or maybe get a bit philosophic. Whenever you apply mathematics in some science or anywhere, it basically all boils down to solving equations. So we have some equation which is of the form, let's say, very general, just very abstract, f of x is equal to y. And the trouble always starts when we kind of have given some y and we are asking, is there an x which solves this equation where f is some function that we have given. So how to solve equations? This is basically the main question underlying all kinds of mathematics and all kinds of applications. And the trouble with mathematics is that there is no general method of solving equations, of course, because this can be very complicated. And if f is a complicated function, we might have no chance of finding such solutions. So what do we know? We have seen in this course that for systems of linear equations, so in the case that this would be some elements of a vector space, or let's say Rn to be simple, and f was a linear map, then we have really the Gaussian elimination method and so on to compute the solution sets of such equations, or in general to decide if they have solutions or how many solutions they have and so on. Now if f is not linear, if f is just some arbitrary map, some arbitrary function, this might become a very complicated question. So for example, a very concrete system of equations, and this is an example that we shall later on see, that we can really say something about the solutions with the so-called inverse function theorem, which we shall see in the next section. Namely the following, consider the system of equations. Let's say we have two variables x and y, and we want that x squared plus y squared plus x squared cosine y plus, minus the sine of x squared equals u, and the sine of x plus xy equals v, where u and v are just some given real numbers that are kind of, I don't know, 1 and 2 or whatever, so some numbers that we can just write down there. And so if I now ask you, so if I write down some u and v, can you find some x and y which solve these equations simultaneously? And probably the answer would be, no idea. I mean, there's no obvious way of how to solve such an equation. I mean, there's no idea how to even tackle this. I mean, you could try to resolve something by x and by y, but you see that both x and y appear there on their own and as an argument of sine and cosine. So with arc sine, arc cosine, this also wouldn't really help. So we have no idea. So in general, with our knowledge so far, we have learned a lot of mathematics and a lot of theory, but we cannot tell if this system has an equation, has a solution or not. So we will see later on that we can say something about the solutions, but this will be an example of a very complicated set of equations. Okay, so this is the idea. We want to solve complicated equations and see kind of, take a look at some theorems which are very deep and show us for some general classes of maps if we have solutions of equations. The first one we shall tackle is a bit different than the other ones, namely the so-called Banach fixed point theorem. This is actually a statement about metric spaces. And this is also the title of this section and also the title of the video you're watching, I guess. The Banach fixed point theorem. The same Banach whom the Banach spaces are named after, an important Polish mathematician. Banach fixed point theorem. Okay, and this is now a statement about maps on metric spaces, which, if we see this later on, at first sight, it has nothing to do with solutions of equations, but we shall see that this has really some interesting applications. Namely, let me write down a concrete problem. So, question. Is there a bounded function not necessarily continuous or anything, just a bounded function from R to R, such that the following equation is satisfied. F of 2x equals 2f of x plus sine x. And this for all x in R simultaneously. Again, no idea. So this, would be hard to tell. If the sign wasn't there, this would be just linearity, and so we would say, okay, linear maps do. But I mean, adding the sign, there's no chance of saying of saying explicitly how such a solution should look like with our knowledge that we have so far. And the interesting thing is, this is the question here. So let's put also a question mark. And by the end of the section, we shall be able to answer this question. And so we will see that there is such a function, and we will also have a recipe of how this function should be defined. And we can kind of, at least approximate this function very nicely. Okay, so let's first trace this back. So we trace this back to this Banach fixed point theorem, and this is the theorem I will state now, which upon first sight has nothing to do with this problem here. Namely, assume we have a metric space which is a complete. Again, a complete metric space means every Cauchy sequence in the metric space converges. This is what we discussed in chapter 11. So this is a complete metric space. And assume we have a map which goes from X to itself, which I also call F. Sorry for the notational confusion, I hope there is none. So the map from the metric space to itself, and let this be given so that there exists a constant C between 0 and 1, with 0 might be included but 1 not, so smaller than 1, such that the distance of f of x1 and f of x2 for any 2 points x1 and x2 is smaller than or equal to c times d of x1, x2, and this holds for all x1, x2 in x. So this looks familiar. This is the condition for Lipschitz continuity, but here we make the additional assumption that c is smaller than 1. So this is making, so this means f is making distances shorter. If 2 points had some distance before, c times this will be smaller, so this means the distance of the image of the images of the 2 points will be smaller than the original distance. So kind of f is shrinking things. That's the idea there. Also one piece of notation. Such an f, so for which there is such a constant smaller than 1, is also called contraction of x. Okay. Oh, sorry, I didn't write the name. This is the Banach fixed point theorem, which is now to come. And in some English language textbooks, this has a different name. This is sometimes also called the contraction principle, or contraction theorem, depending on which book. So in some of the references I gave you, it has the name contraction principle, so this is the same result that we're referring to. I think in Europe, Banach fixed point theorem is more common than in the States, but I don't know. So this is a contraction of x. So if this holds, if we have such a Lipschitz continuity condition with constant smaller than 1, then the conclusion, then f has a unique fixed point, and I will define what this is, i.e. there exists a unique, using this notation, point which I shall call x star as an index in X, which is a fixed point, and this means f of x star is x star. The point is mapped onto itself. So for any such contraction of a complete metric space, there is a unique point which is mapped onto itself by this contraction. So a very intuitive example is kind of some standard example of the Banach fixed point principle, just heuristically. Assume we have a map. I would now be in the Zoom and would have a map of Leipzig in my hands. Sorry, I forgot about your age. Yeah, you're quite young. Back in the days, in the ancient times, when there was no internet, no Google Maps, Apple Maps, whatever, we had maps. Those were printed on paper, and it would be like Google Maps in fixed zoom printed on paper. And it needed no battery, no charging, and you could use this and you would see the map in there in this fixed zoom setting, and you could buy them in stores. Those, dear children, were maps. Okay, if I would now be in Leipzig and put, so I'm where I'm now, and I would now put on the floor, on the table, I would spread a map of Leipzig. This map would be actually the contraction of Leipzig. So like every point in Leipzig would be visible on there, and this would be in Leipzig somewhere. So I could just associate with each point, just as a point, say in R2. So imagine all of Leipzig as in two-dimensional coordinates, and I would give to each point the coordinates which it has on the maps as it is lying here in the room. Then this would be a contraction because distances are shrinking on the map. So putting Leipzig all onto a map would be a contraction, and now the Banach fixed point theorem says there is a unique fixed point, so there is a unique point on this map which lies exactly on top of itself when it lies here in this room. One particular point which is precisely on this and not a single point more. So precisely one point. That's kind of an interesting application. It's one of these applications which is beautiful but useless, but this is kind of, to get the idea, this is interesting to see the Banach, to imagine what the Banach fixed point theorem looks like. Like if, just take a thought about, I don't know, if you're sitting in front of a computer now, just open Google Maps and open some map where your room is, the room you're in is on the map. Maybe you can then see, you can imagine that there's only one point which is precisely there where your computer is, so in real time. Okay, anyway. This would be the idea for the Banach fixed point theorem. So let's first prove this theorem. And this is now really nice and abstract in metric spaces. And the proof is actually not that hard, but it's beautiful, actually. Okay, we need to show the unique existence of a fixed point. So let's start with uniqueness. This is the easier part. So let's assume we have two fixed points. Let's say x1, x2 in X. And say that both of them are fixed points, so f of x1 is x1 and f of x2 is x2. Okay, and so for uniqueness we just need to show that these 2 points must coincide. Okay, and there's a simple way to do so, namely we consider the distance of these points. So we know d of x1, x2 is now, since this is a fixed point, this is the same as d of f of x1, f of x2, since these are the same points. But now we can apply the inequality which defines the contraction, so this here, which means this is smaller than or equal to c times d of x1, x2. Okay, here we have d of x1, x2, here we have c times d of x1, x2. So let's bring this to the other side. Then we get that 1 minus c times d x1, x2 must be smaller than or equal to 0. Okay, but by assumption c is strictly smaller than 1. So this number here is positive. This number here is a metric. We know that metrics have this property, is by definition non-negative. So this is positive, this is non-negative, but this should be non-positive, so smaller than or equal to 0. So the only way this can happen is if this is already equal to 0, but this only happens if this is equal to 0. So this implies d of x1, x2 is 0, but by the first property of a metric, the distance between 2 points is 0, means x1 is equal to x2. So these 2 points must coincide. So this shows the uniqueness of our fixed point, simply from this contraction argument. Okay, so we need to discuss the existence. And this proof is also interesting because this kind of gives us also a way of how to find this fixed point, because the theorem so far abstractly only says there is a unique fixed point, but we have no idea what it is. But the proof is really constructive. Namely, we start with an arbitrary point in x, which we call x0, and we define a sequence. A sequence xn in x as follows, namely recursively, as we used to do several times in the last semester for real sequences, and we can do the same recursion principles for arbitrary sequences. So, namely the following way. The first term of the sequence x1 is just our starting point x0, and xn plus 1 is simply given as f of xn for all n in n. So we start with a point, apply f, so x2 is f of x1, f3 is f of x2, which is f of x1. So f4 is then f of x1, and so on. So we just apply f many times. And this is the short way of writing this, defining this recursively. Okay, this is now so we start with an arbitrary point and consider this by just applying f and f and f all over again. Now, then, for all n bigger than or equal to 2, we compute the following. If we take the distance of the n plus first term of the sequence and the nth term of the element of the sequence, this is now by definition d of f of xn, f of xn minus 1, but now we use the contraction argument, and so the contraction definition, this is smaller than or equal to c times d of xn minus 1. So let me write this once explicitly. Sorry, again, d xn plus 1 xn is smaller than or equal to c times d of xn minus 1 for all n in n bigger than 2. Okay, this holds for every n. So if we take this difference here from 2 subsequent elements of the sequence, this is smaller than or equal to c times the 2 elements before. And now it's of course clear what we can do. We can iterate this. Here we can use this then the same inequality again and again and again and again, and take a look what this looks like. So this means d of xn plus 1 xn is smaller than this, but if we now apply the inequality again to this part here, means we get c smaller than or equal to c squared times d xn minus 1 xn minus 2. And again, smaller than or equal to c3 d of xn minus 2 xn minus 3. And so on, and we can do this until we arrive at the first elements of the sequence. So we have d of x2, x1, and we see that, here, so with n plus 1 we started, so from n plus 1 to n we go by 1, and then we have to go to n minus 1, and so on, and so on. And it turned out if we count already, this should be c to the n minus 1, so because this is n minus 1 many iterations of this formula. So we have this. So let me also write this down explicitly. d of xn plus 1 xn is smaller than or equal to cn minus 1 times d x2 x1, and this number I shall just call a. So this is c to the n minus 1 times a. And this is somehow good news, because we wanted to use the we want to use the completeness of the metric space there. And the idea is now that we want to show that this sequence that we are studying here converges to a fixed point. So that the limit, this converges, that the limit must be a fixed point. In order for this to converge, since we have a complete metric space, it suffices to show that we have a Cauchy sequence. So for Cauchy sequence, we need to show that for kind of high indices, the distance of the elements of the sequence needs to be small. And here we see that the distance of at least two subsequent elements is smaller than this here, and we see that since C is a number which is strictly smaller than 1, if n becomes bigger and bigger, this tends to 0, which means these distances become very small. And this will be enough to determine, to compute that this is a Cauchy sequence, but I need to erase first to present you a proof of that fact. This is where we left off. We have actually only shown this for n bigger than or equal to 2, but for n equals 1, this is obviously true because we have the same term on both sides. Now, what can we do with this? We have these estimates that the distance between two subsequent elements is small, but to show that something is a Cauchy sequence, we of course need to have bigger index differences. So we need to have, so assume we have some arbitrary m and n in n, and we just need to decide which one is bigger, m smaller than n. Then this inequality is labeled star. So we want to show that the distance dxn xm becomes small, very roughly. So what can we say about this? This is not the difference of two subsequent elements, but we can make it a difference, or not as different of subsequent elements, but a sum of differences of subsequent elements. Namely, by simply applying the triangle inequality. But the triangle inequality, this is smaller than or equal to dxn to xn minus 1 plus dxn minus 1 xm. So here we have two subsequent elements, and here we have still different indices, but we kind of lowered this index here, and we can just do this again and again and again, apply this now to this term and so on, until we really achieve at m plus 1 here. So this, after iterating this is the same as, not the same, this is smaller than or equal to the sum from k equals 1 to n minus m of d x m plus k and x m plus k minus 1. Just a little complicated way of writing the indices, but this is precisely what we had. Now, these here we can estimate. For this, we can now apply this inequality that we had. So for each of the summands, so this is smaller than or equal to the sum of k from 1 to n minus m. And now each of these is estimated by C2, and now we just need to get the index right. So here we had basically here, the difference here, this is the first index minus 2. So we have this minus 2, which is C to the m plus k minus 2 times a. Yeah, that's it. So this is the difference of this. Now, let's simplify things a bit. This is, maybe not simplify, but reformulate, because we can now apply something we already know to this equation. And now factor out one particular term. Namely, we have c to the m minus 1 as a constant factor times the sum from 1 to n minus 2 c to the k minus 1. For this, we can now perform an index shift. Or basically, no, we don't need to do this. Basically, we can, already take the full thing here. Or no, maybe let's simplify things a bit. Sorry, c to the m minus 1. And now the sum, shifting the index by 1, we start with 0 and go to n minus 3. Well, why have I 2? N minus m, I'm sorry about that. It's just, n minus m. And so here it's n minus m minus 1, c to the k. So, but since c is a non-negative times a, But since k is a non-negative number, this is smaller than or equal to c to the m minus 1 times the sum k from 0 to infinity, and then you're taking the whole series, c to the k times a. And if you take a look at this, this is the geometric series in C, and since c is smaller than 1, we know from mathematics 1 that this converges. And we also have a formula for this expression, so this is here just geometric series. This is 1 over 1 minus c, this expression here, so the whole thing is c to the m minus 1 over 1 minus c times a. Okay, so let me summarize what we've shown. Sorry, I was a bit hasty. So we've shown that d of xn xm is smaller than or equal to c to the m minus 1 divided by n1 minus c times a. A was this fixed number, this distance of the first two elements, which is not really relevant for us for how big this is. So this is, this inequality holds for all m n in n with m smaller than or equal to n. Okay, now this is what we got. And here we also see, I mean, we have a and 1 minus c as constant terms, but we see if m becomes bigger and bigger and bigger, since c is smaller than 1 and bigger than 0, this will tend to 0. So we see this becomes very, very small, which already gives us that we have a Cauchy sequence. So, yeah, to really formalize now that we have a Cauchy sequence, we just need to bring some epsilons in there and to do the formal, showing formally that this becomes smaller than epsilon, and let's do so. Given epsilon bigger than 0, there exists some number n0 in n such that c to the n0 minus 1 times a is smaller than 1 minus c times epsilon. This becomes very, very, very small. And of course, if n becomes bigger, this becomes even smaller. So this means for all m and n in n with with m bigger than or equal to n0 and n bigger than or equal to n0, we get that d of xn xm, and now it doesn't matter which one is the smallest because they have both bigger than n0, so we get that this is smaller than c to the n minus 1, n0 minus 1 over 1 minus c times a, and this is now by construction smaller than epsilon. So this means the sequence xn is a Cauchy sequence. And now, since X is a complete metric space, so here we need the completeness, whoops, it converges. Converges in X. And now I claim that the limit of the sequence is a fixed point, and this is what we need to prove. So let X star denote the limit of the sequence xn. Sorry about that. Now x star is the limit of the sequence, which we have now shown to exist. But how can we show that it is a fixed point? First of all, I haven't formally proven this, but as for the real numbers or for complex numbers and sequences in there, subsequences or convergent sequences always converge against the same limit. This is kind of really easy to see. So then in particular, we observe that if we take the following subsequence, we take the limit n to infinity of x n plus 1. So everything shifted by 1, just dropping the first element of the sequence. This is technically speaking a subsequence. So, but we know that this converges. But by definition of our sequence, this was nothing but f of xn. So we now have to find out what f does to limits, very roughly. And the idea is now, since f is a contraction, we've particularly follows that f is Lipschitz continuous. And we've seen that all Lipschitz continuous maps between metric spaces are continuous. So f is continuous in the conventional sense. This was Theorem 1139. Now, but since f is continuous, we obtain that f is compatible with limits very roughly. Namely, we get that x star, this is now the limit as n goes to infinity of x n plus 1, which is just by definition of the sequence, nothing but the limit of, as n goes to infinity of f of x n, and now sequential continuity. If we apply this result by sequential continuity, this means that the limit of the images of f is the same as f of the limit. So this is Theorem 1130. So sequential continuity this is the same as f of the limit as n goes to infinity of xn, and this is by definition f of x star. So x star is indeed a fixed point. So x star is a fixed point of f, and this is all I wanted to show. So this gives the existence of a fixed point. Uniqueness has been shown before, so this proves Banach's fixed point theorem. Okay, now, which is now implicit in this proof is that we already know how to construct our fixed point, or how to find such a fixed point explicitly, and by just applying the method we just used in the following way. So, remark 13.2. So, given a contraction, let me just write this. So, Lipschitz continuous with Lipschitz constant smaller than 1, given a contraction f from x to x, and x0 and x arbitrary, the fixed point of x, of f, is given as follows. We have seen that we have this as the limit of this certain sequence, and the sequence was just given by iteratively applying f again and again and again. And if we just write this slightly differently, namely here in general, if we have such a map, we can just define this as the limit as n goes to infinity of f to the n of x0, where f to the n is just the n-fold composition. So f to the n is just f composed with f, composed with f, and so on, n many times. Okay, and this is something we might be able to compute. We just start with some particular point, maybe something very simple if our metric space is simple. And then if we know how f is given explicitly, then we can just basically compute the sequence and maybe compute the limit explicitly. So this is just something we can observe, and this follows directly from this method of proof. This is basically a nice lesson why you should also be interested in proofs and not just in theorems and statements, because they really tell us how things work. Okay, let's go back to the example I had in the beginning. So example 13.3. Let me write this down again. So the question was, is there a function from R to R which is bounded with f of 2x is 2f of x plus sine x for all x in R. Okay, the obvious question, what on earth does this have to do with the Banach fixed point theorem? And this is probably very non-obvious at this point. Let me rephrase this equation a bit. If we just play around and if we just bring the sine over to the other side and then divide everything by 2, we get this is the same as f of x is 1/2 f of 2x minus sine x for all x in R. Okay, now this already looks a bit like here's some f and here's something that is being done with f. And this is the idea now that in this way we can make this a fixed point problem, namely the following way. We know that the space of bounded functions with the supremum norm, the sup norm here. This is a Banach space. This is what we've seen. Is a Banach space. This is what I've proven in chapter 11. And we now consider the following. We just consider the map capital F, which goes from B, R, R to itself. Oh yeah, Banach space, so complete norm vector space. In particular, if we take the metric which is induced by the norm, it's a complete metric space. So this is where the Banach fixed point theorem can be applied in this setting in principle. So let's consider this map capital F, which is now given by f of a map f. So this is again a function from R to R, and we want to define this for every x as just the right-hand side of this. 1/2 f of 2x minus sine x, and this for all x in R. Yeah, like this. Okay. So this is the definition of capital F. So if this equation is then labeled, we have star already, maybe, yeah, that was, we call this double star, okay, then F satisfies this equation double star if and only if, and now just by definition of this capital F, if capital F of small f is equal to F. This is just a rephrasal of this equivalent formulation here. Okay, so if this holds, in other words, F is a fixed point of capital F. So we have formulated this as a fixed point problem. So fixed point problem always means we want to find a fixed point, or we are interested in the question if there exists a fixed point of a map. And this is a standard way. Now we have formulated this as a fixed point problem. And so to apply Banach's fixed point theorem, we just need to show that this capital F is a contraction on this metric space here. This is what I should do after erasing. And let me just give you on this way that many problems in geometry or in analysis can be kind of rephrased as fixed point problems. And there are more fixed point theorems than Banach's one. There's Brouwer's fixed point theorem and others. So there's fixed point theory is kind of a whole field of itself, but there are a lot of different approaches. And so it's usually often a good idea to formulate something or to reformulate a given problem as a fixed point problem. And so using all the machinery we have to find fixed points. So this is why this is a good approach. Okay, so let me show this then. And then we only have to show that F is a contraction, which is not that difficult as we shall see. And then we automatically know that we have a fixed point. So that means we have there exists a solution of this complicated equation. Okay, let me erase and then we'll go on. Let's show that it's a contraction. So we need to consider the metric induced by the norm. This means we need to consider for all two elements of the metric space, meaning F and G in the space BRR. We have to check that, we have to check these differences here, F of F minus F of G in the norm, where we have in this time the sup norm. So just by definition, this difference here, I mean, we need to show that this is smaller than or equal to the difference, the norm of the difference of F and G, times a constant which is smaller than 1. So let's just compute. This is by definition the supremum over all x in R of F of x minus F of G of x. Let's put in some more parentheses. Okay, like this. And just to remind you, F of x is 1/2 F of 2x minus the sine of x. And so, like that. Okay, so if we have two terms, so F of F and F of G, we see that both have one term in common, namely minus 1/2 sine x. And so if we subtract the two of them for each x, we see that these sine terms completely cancel each other out. So this is the supremum over all x in R, and what remains is 1/2 F of 2x minus 1/2 G of 2x to the absolute value. So this, of course, there we have a constant 1/2, which we could then put out of there, and since it's the absolute value, we can just put the 1/2 out of the absolute value altogether. So this is the same as the supremum over all x in R, F of 2x minus G of 2x. And if we take a look at here, if we go over all x in R, it doesn't matter if the 2 is there. We just check the supremum, and we are scanning through all x in R. Here we're just basically scanning with double speed. So if we just consider the supremum of this expression, this is the same as 1/2 the supremum over all x in R of this expression, F of x minus G of x. And if we take a look at what's here now, this is simply the sup norm of F minus G. So here we've shown that this difference here is even equal to 1/2 of the difference of F minus G to the norm. And we only need smaller than or equal to. So this implies, 1/2 is clearly smaller than 1. So F is a contraction. So by Banach fixed point theorem, fixed point theorem, let me abbreviate it like this. It follows that there exists a unique fixed point of F. And this implies that this equation double star has a unique solution. So there's a unique bounded function. I mean, this mysterious equation where we had no idea if solutions exist or how many or something, now we can say there exists a unique solution of this equation. Unique solution in the space of bounded functions from R to R. Now, if we wanted to compute this function explicitly, we can then use the methods from the previous remark, namely by just starting with one particular element and then iterating f. For example, so let's call this unique solution f star. So by remark 13.2, we could also compute f star as the limit n to infinity of fn, where we just start with f1 of x to be, so we just need to apply capital F to a particular element, and there's a particularly simple element of the in the space of bounded function, namely 0. So f of 0 applied to x, and this would just be minus 1/2 of the sine of x. Then f2 of x would be f of this here, of f1 of x. So 1/2 of this expression of 2x minus sine again, so here we would get 1/2, and then this here in 2x, so minus 1/2 sinus of 2x, and then minus sine x, which gives minus 1/4 of sine 2x minus 1/2 sine x. And we could go on and on, so f3 of x is f of f2. Oh, sorry, here the parentheses are wrong, like this. Okay, and here like this in x. So this would be this time, so minus, 1/2 of this function applied to 2x, which would give minus 1/4 sine, and now we have to double 4x. Minus 1/2 sine 2x minus sine x, and if we would now compute everything, this is minus 1/8 sine of 4x minus 1/4 sine 2x minus sine 1/2 sine x, and so on and so on and so on. And you could then get that fn, this is some formula we could prove by induction, which we don't do. This would be minus the sum, and now I have to pay attention that I get it right, from k equals 1 to n, yes, of 1/2 to the k, sine of 2 times k minus 1 times x. I think this should be correct. Wait, no, this is not correct for, wait, not 2 times k minus 1. Nonsense. 2 to the power of k minus 1. Sorry, like this. This should be correct. And then we could show that this converges, and this would be kind of a series of functions. This is a notion that I have skipped in this course because it was not too relevant for you, so we could really, you could also, instead of just considering sequences of functions, we can then also study series of functions, but I have stopped at this point, but this is how you could get the limit, and this is how you could get some formula, and also compute this approximately. So you could see that this converges, and for example, you could then compute fn for n equals 5,000 or something to get a very good impression of what this fixed point would look like. So formulas like this help us not in, maybe not in determining the fixed point explicitly, which might be hard, but at least to compute this approximately. Okay, this was the example for the Banach fixed point theorem, and now we come to the first really big calculus theorem, namely the inverse function theorem. See you in the next section.